In discussing computer programming principles, certainly hardware plays an important role, as well as the techniques of problem solving. But today, we will concentrate on the history of programming as well as programming language development. Generally speaking, there were three stages to programming language development. The first might be called machine language. People within machine language first use binary. That is made up of the digits 0 through 1. Later on, they were able to code in decimal, but still, strictly speaking, sticking to numeric designations. This was followed by a symbolic programming process, where mnemonic operation codes like CLA, standing for clear and add, were used. Following that, the introduction of the notion of a symbolic address, some place in the machine that you would clear and add from. In this case, we're clearing and adding from a location called gross. Finally, we developed problem-oriented languages which permitted the programmer to use statements like A equal B plus C in one language and add others to REGHRS, which might stand for regular hours, giving total hours. Now let's look at a typical machine, a hypothetical machine, which will help us understand the development of binary operation codes and binary addresses. In describing our machine, let's assume we have a 2-bit operation code. By bit, I mean a binary digit. I can have either of the bits 0 or 1 in those locations. Likewise, I have a 3-bit operand, any one of the digits 0 through 1 in any one of these locations. And finally, let's assume I have a 4-bit accumulator, the place where the results are going to go, where a 0 or 1 can appear in any one of those positions. Now, let's look at the opcodes that will make up our machine. This is the repertoire of instructions which we'll permit in our machine. Well, since we only have two slots reserved for the operation code, these are the only opcodes that are available to our machine. And let's assume that 00 means stop, 01 means load, 10 means add, and 11 means store. Now, in addition to the opcode, let's look at the memory that we'll have reserved in our machine. Since we only reserved 3 digits for the size of a memory in our machine, we can only have 8 possible positions inside the machine. Now, let's combine the opcode and the operand and look at a typical instruction. For example, the instruction which is made up of the opcode 10 and the operand 100 would mean add the contents of location 100 to the accumulator. If location 100 had the combination of bits 101 in it, this would be added to the accumulator. One of the most difficult concepts in first coming to grips with a programming language is to distinguish between the name of the location, in this case 100, and its contents, in this case 101. Now let's look at a machine language program for this particular machine, this very simple machine. Let's assume that we want to add the contents of a location 100 to the contents of location 101 and store the results in location 110. And this would be the program that would do that. Recall 01 meant to clear and add the contents of 100 to the accumulator. 10 meant to add the contents of 101 to what was already in the accumulator, which came out of 100, and 11 meant to store what was in the accumulator into core storage location 110. Now, a symbolic version of this same program might look like the following. Load the contents of a location whose name is dog, add the contents of a location whose name is cat into the accumulator. Recall that the contents of dog was put into the accumulator by the load instruction. And finally, store the contents in a place called rat, followed finally by a stop code. Now this jump from machine language to symbolic programming was an enormous jump. People, programmers in the early days, could not consistently code in binary. It required too much concentration. And it's this big jump from being able to go from a machine language made up of zeros and ones to a symbolic language made up of mnemonics that trigger the memory, which really helped programming along. But still, programmers were held up in their progress. Still, they had a great deal of difficulty to add two numbers, to have to write down these 7 different commands, as it were. So let's look at what might be called a Fortran version of this same program, the program that we were looking at a minute ago, in both machine language and in symbolic code. It would simply read rat is equal to dog plus cat, and would mean as before, take the contents of a location known as dog, add to it the contents of a location whose name is cat, and store the results in a location whose name is rat. Now, the process of going from the symbolic code to the binary code is known as assembling. You assemble the binary code for the particular machine. And that process is done by a program that's known as an assembler. And the assembler then is the translator that takes the symbolic code and translates it into machine language. The very first assembler was a gigantic step forward, as I said before, for programmers. Now, from this assembling process, we went into this higher level language which we looked at before, where rat was equal to dog plus cat. And this is just one example of a typical statement in the first problem-oriented language that we used here in America, namely Fortran. Now, Fortran is a mnemonic that stands for Formula Translator. It was used by mathematicians to handle their problems. Now, this business of Fortran stands for 2 different things, really. Fortran is a language, and Fortran is the name of a translator itself. In particular, this translator is called a compiler, the Fortran compiler. Now, what is the purpose of the Fortran compiler? The Fortran compiler is a program to translate Fortran statements to the machine language version of the same program. In actuality, in the very early days, what you did first was translate from the Fortran statement to the assembly language version of the same program, and then you took the assembly language version of that program, put it through the assembler, and got the machine language version of the program out. Note that for every machine you needed a separate assembler. For every machine you needed a separate compiler, but that the language remained the same. Fortran was Fortran throughout the world, but the Fortran compiler that translated from that language was different for each machine. Now, within the language of Fortran, let's look at it a little more closely. We have various types of statements. The first being the arithmetic and assignment statements of the type A equals B plus C. We have more complex expressions, arithmetic expressions, which can take on a form including multiplication signs and division signs. Now let's look at the more complicated arithmetic expressions. Here we have the slash being the Fortran symbol for the division sign, and the asterisk being the Fortran symbol for multiplication. And because of the fact we have we have to associate some things first, it's a Fortran rule that first we go from left to right, and the first thing we'll do is divide before we multiply. Now let's look at an even more complex version of an arithmetic expression. Here we have a sequence of variables being added, divided, multiplied, and we have a double asterisk, which in Fortran means raising a number to a power. So this arithmetic expression in Fortran means this in ordinary algebra, if in ordinary algebra you remember that the slash stands for division and the asterisk for multiplication. Now let's look at what the programmer would do on his way to the computer. He would code this statement on a coding form like we have here. This is a Fortran coding form. It's a form specifically designed for the Fortran language. Statements begin in column 7, and you allow one letter or one symbol for each column. What's more, recall that in Fortran we're only dealing with capital letters. There are no small letters being used in Fortran. This coding form would then be sent to a key punch operator who would punch cards from the coding form. Now let's look at another type statement in Fortran, a control statement. Here is an example of a control statement. It changes the control of the program. It changes the direction in which the program goes. And this particular statement reads, if A is greater than or equal to B, go to 6. What it means is, if the contents of location A is greater than B, you go to a statement whose number is 6. If it isn't, if A isn't greater than or equal to B, you do the next sequential statement. Now another type of statement that's used in Fortran are input-output statements. They generally look like read and write. They generally have two operands. The operand standing for, the first operand standing for the device you're going to read from. The number 5 might mean you're going to read from a card reader. It might mean you're going to read from a tape. But it does mean the device you're going to read from. The number 6 refers to a picture of the information that sits on the device you're going to read from. We say that's a reference to a format statement. The format statement will tell us what the information looks like. Now, in format statements, they actually have the word format written right in it. A format statement was numbered, has a number associated with it, and then it has a number of codes which tell me the type of information that's in the input medium. In this particular case, it says that I have a 3-digit field which are all numeric, followed by a 2-digit field which are integer types. This here are the types of numbers that have decimal points in them. These are the types of numbers that are just integers. Now the next type of statements that are available in the Fortran language are the specification type statements. This is an example. The word real tells the computer that the variable that follows real, I might say real A, real B, is a real variable. It tells the computer the type of storage it should reserve for the variable known as A or B. Now let's look at a more complex type of statement available in Fortran. It's the subprogramming statements. Subprogramming is a major concept in programming. It's the ability to take a very large problem and break it up into little pieces. The little pieces are called subprograms, and in particular, the word that's generally used in Fortran for subprograms is subroutine. The name of the subroutine is cat. It has a collection of arguments, A, B, and C. For example, the subroutine cat might just add the two quantities A and B together and bring the result back in location C. Now, as we have all these types of statements in Fortran, let's look at the entire translation process again. What happens is we take our source program made up of these types of statements. Within the computer is the language translator. In our particular case, it will be the Fortran compiler. Through the source program, these Fortran statements come through. The language translator comes in, translates them, and puts out an object program. The object program being the machine language version of the Fortran program that we just wrote. Outside here also we get a program listing of our particular program we've just written. Now let's go through a little small problem and look at the corresponding Fortran version of this problem. Supposing we have the problem of adding, reading in two variables, one named A, another named B, dividing A by B and adding 1.5 to the result, and storing the result in X and printing out the result. Well, let's look at the Fortran coding form that represents the solution to this particular simple job. I'm using a little modified version of Fortran here, but it'll give you the general idea. Here we have the job name, and this is a message to the operating system that I have a Fortran program coming up. And this is the programmer's name, let it be John Doe. Well, we have three specification statements. We're saying that the variables A, B, and X are all real. And we're saying let's read A, let's read B. Then we're going to take A and divide it by B, add 1.5 to it, and store the result in X. Finally, we're going to print out X and return to the operating system, and we're through. Now the dollar entry card here tells me this is the data that is going to be used by this program. Now what will happen is we have two steps, remember, in handling programming. First the translation and then the execution. Now the data point 55 is read into the variable whose name is A. The data value 11 is read into the variable whose name is B. We take 55 divided by 11, getting 5, add 1.5 to it, getting 6.5. Store the result in X, and we print out the value 6.x at the end of our program. Realize now, no matter what values I put into the following the data entry cards, I would get A divided by B plus 1.5 being printed out. Now let's look at a little more complicated version of this same translation execution phase. To repeat it so we understand it, we have both the source program followed by our data. First, the source program is read in, translated by the Fortran translator, put out as an object program. Next, the object program is read into the machine, the data is pulled through the object program, and both the listing and the results, namely in our case 6.5, would be printed out. Okay, let's look at a more complicated mathematical problem. Namely, let's find the area of this particular geometric figure. On input, we are given the height of this figure and the width of this figure. Now, the way the program is going to work, we're going to find the area of this rectangle and subtract the area of that semicircle. So let's look at a flow chart that will help us set up the steps to find the area of this geometric figure. We begin by reading into a variable into the program the value of pi, namely 3.141593. We'll next read the height, then we'll read the width, then we'll calculate the area of that large rectangle, namely, and we'll call it R, namely the height times the width. Now we have to subtract the area of that semicircle. Now recall the area of a circle is equal to pi r squared, and pi we know already. Now we only have the width. Therefore, we must take the radius and divide the radius by 2, therefore giving us the area of the full circle to be given by the formula pi w squared over 4. Since we only want half the circle, therefore we want to use pi w squared over 8. And this is the value we will be subtracting here, pi w squared over 8. Therefore, we will now take the value of the rectangle, the area of the rectangle, whose area is stored in the variable name r, subtract from it the area of the semicircle, whose value is stored in s, put the results in f, print out the original height, the original width, and the new value of our figure, and return to the operating system. Let's look at the coding form for this particular program. We have again real height, real width, real pi, and so on. We've read it, we've put in the value of pi, we read the height, we read the width, we computed this value, the area of the rectangle, the height times the width with the asterisk. We've subtracted the area of that semicircle, which was pi, 3.14, times the width squared, divided by 8. We've taken the area of the rectangle, subtracted the area of the semicircle, put the result in a variable whose name is area, printed out our height, width, and area, returned, and finished the job. We've been discussing some of the rudiments of the Fortran language. This language was invented in about 1954, became largely used in 1957, and really made its impact on the market about 1961. But the businessman, he was not very satisfied with this programming language. He needed something more, something he could get his hands on a little better. Well, late in the 50s, the Department of Defense brought together some of the major manufacturers of computers and said, we want a language which will serve our purposes. This language that they wanted to design had to have a number of features in it. In particular, it had to be self-documenting. It was hard for the businessman to read the COBOL version of the Fortran version of a program. There was too much mathematics there. He wanted to understand what the programmer was doing. He wanted also to have a standard language. Fortran started to have a number of dialects, and still does have a number of dialects around the country. And so the Department of Defense wanted to standardize a language which would be used throughout the country. And they came upon this language, COBOL, and it had these properties. Now, COBOL stands for Common Business Oriented Language because of the reasons that I've been trying to describe before, the communality of it throughout the business community. Now, COBOL, like Fortran, has a number of types of statements. We won't be able to see all of COBOL like we weren't able to see and understand all of Fortran. We want to get an idea, though, of the types of statements that go to make up the language, any language, as a matter of fact. Well, COBOL has input-output statements also. They have arithmetic statements. Now let's look a little closely at the arithmetic statements. These are the types of things that you'd say in COBOL. You could say add A, comma, B, C, or add A, comma, B to C. Each of these types of expressions, but they result in different things. Let's look at the first one. Saying add A, comma, B, comma, C means take the value of A, take the value of B, add them together, add the value of C, and store the result in C. It's the same thing happens if we use this other version, add A, comma, B to C. If we use the version add A, comma, B, C giving D, we will add A to B to C and store the results in a variable whose name is D. Notice in the first two cases we lost the contents of C. Well, these various arithmetic commands are a little bit easier for the businessman to read, and also there's a little more communication between the programmer and the person who asked for the program. Now, just as we had to take the Fortran arithmetic expression and put it on a Fortran coding sheet, so also we should take the COBOL arithmetic statements and put them on a COBOL coding sheet. Here we have a different format to the coding sheet. Notice that the commands begin in column 12, at least this type of command. And we have add A to B giving C being spaced out across the coding form. This, of course, would have to go through the key punch process on its way to the computer, just as in Fortran. Now, as we have arithmetic statements in Fortran and COBOL, so also we have input-output statements in COBOL. In particular, we have the read command. Look, you can see by its very nature that there's more communication in the read commands. Read transaction record means more than just read T or read A or read B. It tells the person who's reading the program a little more information. Likewise, as we have read in Fortran, and read in COBOL, we have write in Fortran, we have write in COBOL. And again, notice that it has more communication between the writer of the program and the reader of the program. In Fortran, we had conditional statements, the if statements. Likewise, in COBOL, we have conditional statements. The conditional statement takes pretty much the same form in COBOL as it does in Fortran, but it has, again, more communication. Here we have, if rate is less than 8, go to accept routine. Notice before it was if A is greater than or equal to B, before being in Fortran, that is. And look how much more communication we have in this sentence structure than we had in Fortran. Now let's look at a coding sheet for a larger COBOL program. We'll just look at the skeleton of this program. It's a file searching program, but that's not important. A COBOL program is generally divided into 4 divisions: the identification division, the environment division, the data division, and the procedure division. In the identification division, you have the title of the program, the author of the program, the date the program was written, and what have you. In the environment division, you have the computer on which the program was going to be compiled, as well as the computer on which the program is going to be run. In the data division, you have a picture of the data, the ingredients that go to make up the program. Recall the analogy between the ingredients in a recipe and the ingredients in COBOL as we have it here. Now, the guts of a COBOL program is contained within the procedure division. This is where all the logic goes on. This is where the arithmetic statements are. This is where you have expressions, sentences. Sentences go together to make up paragraphs. Paragraphs go to make up sections. You have the ability to do subprogramming in COBOL, just like you have the ability to do subprogramming in Fortran. And it is, again, just as in COBOL, the ability to break a large program up into pieces that gives a program its nice structure. We've talked about Fortran, we've talked about COBOL. There are many, many programming languages developing in the world. In one count, Gene Samet at IBM in a recent book announced 168 major programming languages. We couldn't possibly talk about them all, nor could we talk about Fortran and COBOL in the detail necessary to let you be a Fortran or COBOL programmer. This takes a full 3-credit course, 6-credit course at a major university, as well as years of experience. But our idea was to give you some concept of what programming is about. What is the future of programming languages? Languages, I believe, will be made more available to all sorts of people, that you won't have to be a programmer to make use of the computer. The language will be built to your particular field. But nevertheless, a concept of a computer, the concepts of language, will be with us for some time to come.